Hi, my name is Shreya. I work with PI Jeffrey Grossman in the Material Science Department at MIT, and I'm pretty excited to share some progress from the past years that we've presented. We are looking at membranes for separations, and our ultimate goal is the reverse osmosis desalination membrane, bring down the cost of desalination, and I'll talk a little bit about that. But what we're looking for right now is what the first market should be for our membranes. What is a lower volume, higher margin, higher dollar value market that could benefit from our membranes as we kind of optimize the process? And so just wanted to just start off with that perception. We're in an El Nino year. California has gotten rain, but still 97% of the state is in a drought right now. A third of which is D4, which is the exceptional drought condition. And so this is a problem that it's a cycle that is longer than a year-long cycle. 1 year of rain isn't going to fix this problem. And when surface water isn't available, you start pulling groundwater. When you pull groundwater, there are regions in the San Joaquin Valley where the land has sunk by 2 inches per month right now from pulling from groundwater depletion. And so, you know, think about that. That's 2 feet a year of the ground sinking, and it's not insignificant, and it's actually doing a lot of things that we don't fully understand. The third way to get water, if you're not taking surface water, you're not taking groundwater, is desalination. And this is roughly what a desalination plant looks like. The water comes in from your bay or from your brackish water. It could be groundwater, but it could be seawater. And then it's treated before it's passed through the reverse osmosis membranes. And that's this little step right here. That's the part that actually takes the salt out of the water. The membranes are made of polymers. They're relatively fragile. And the 0.2 micron active layer that's actually at the surface of the membrane is what's removing the salt from the water. With the membranes that we're talking about removing a significant part of the pretreatment process. And we're doing that because we're using a new mechanism of separation. We're using size exclusion at the reverse osmosis level, which opens up an entirely new category of materials that are just more resilient, more robust, and therefore don't need to be fed with perfectly clean water. When I talk to people about desalination, the first question is inevitably, oh, you're going to reduce the energy costs? Are we going to reduce energy costs? And that's really a big part of the cost, and that's a really absolutely correct perception. But the energy cost isn't actually the part that could be reduced. The energy is pretty close to the thermodynamic limit, whereas the capital cost is the operating costs. The rest of the costs are actually what we think we can remove. So when you look at the breakdown, the pretreatment, the primary treatment part of this step of the desalination process is up to 50% of the total cost. And so when you look at it not from a capital operating, but from a step-by-step process, we can start to see where we can remove costs with membrane technology. So the membrane material that I'm talking about today is graphene oxide. We are looking at other membrane material systems like silicon. We're happy to talk more about that later at our poster. But what we are able to do with this new approach to membranes is by using size exclusion instead of the model that polymer membranes use, we have increased permeability, which means faster flow, fewer membranes, and more effective use of your membrane area material. Because the carbon network of graphene oxide is chemically stable and is not reactive, there's a resistance to chlorine. And this is important because one of the pretreatment steps in a desalination plant is you first chlorinate the water because you have to disinfect it. You then take out all the other things that are in there, organisms, bacteria, viruses, these are all removed. You then dechlorinate the water right before it enters the RO membrane because the chlorine will degrade the RO membrane, pass it through the RO membrane, and then put chlorine back in order to get it into a municipal water supply. So if you can just eliminate that step in of itself, that's just one example of the things that have to be done to protect the membrane. By having a membrane that's resistant to chlorine, you have a higher tolerance against biofouling because now you don't have film growth because of the film is killed off with the chlorine. And because it's not reactive, it's also more robust at high temperatures. And so that opens up classes of separation that are, occur at high temperatures or sterile conditions. And then what we think is really exciting is that the way that we're assembling the membranes, we can change the size. So it's changing the chemistry, and by changing the size, it means we can reject a range of different contaminants. The progress that we've made are by assembling membranes that reject contaminants that are 1.5 nanometers in size, so that's pretty exciting. The films are stable in water, which is obviously very, very important. And we're doing this by assembling the flakes, the graphene oxide flakes, in a layered mechanism, as shown by the photograph, but also by the schematic. And so the interlayer spacing is what we're changing with the chemistry in order to change what we're rejecting across the size spectrum. The other thing that's really important is the way we've designed the process. Every single step of the process is used at large scale for a different application in probably a different order. And so none of the steps, none of the production processes are brand new. And so we're reorganizing things that already are done at scale. So we think that this can be a viable proposition. And as I said, what we're wondering here is what can we start rejecting kind of immediately? What should we optimize for? Chlorine's a really important one for desalination, but are there other chemicals or solvents or other things that we should be focused on in terms of optimization? When I look at the numbers, when I say we remove that dechlorination and rechlorination step, you're saving about $1 million a year in annual operating budget for an average size desalination plant. When you reduce the cleanings that are associated with the membranes that get fouled up, if you can just cut them in half, you're saving another $500,000 on a yearly basis, which for a plant's operating budget is a significant part. But water is a pretty low value, dollar value, not personal value, but dollar value product. And so we're trying to see what we can separate out right now. And so I'd love to talk to you more. We'd like to thank the Deshpande Center, JWAFS, especially our catalyst, Karen Golmar, and also the rest of my team, Brendan and Jatin, who are over here, and Professor Grossman as well. So thank you.